regardless of the level of the other factors. In other words, having diabetes, does that increase your risk of dying regardless of whether you're a male or a female, regardless of whether you're young or old, regardless of whether you've had a history of cardiovascular disease or not? Or does the effect of diabetes change depending on your sex, or depending on your age, or depending on your history of cardiovascular disease? If so, then you have to include what we call interaction terms in our model. And that's something we probably won't get in today, but that's another question to consider. So basically what I want to talk about is trying to decide which of these various ways to represent a confounder in a model can be aided by the fit of a model to a data set. Essentially, we might fit a series of different potential final models to our data set, and then we have to have a way to decide which of these is the best model to go with. So I think that's all I wanted to say with in terms of slides. So what I'm going to try to do is close this, minimize this, turn off my PowerPoint slides. I'm going to try to pull up SAS. So it might take a few seconds for you to catch up to me, but what I've done on my wife's computer is I brought up SAS, and I'm bringing up the program that Erin was running for us the last couple of days. So Erin, if you're still there, can you just give me a heads up that what you see is a SAS program?
I'll just hang on for a second to see if Erin can respond.
Oh, yeah, we just switched to the desktop.
The reason.
Okay, do you see
let me know if you see the SAS window with the program.
Not yet. Okay, it just popped up.
Okay, we'll wait a second.
Okay, we'll wait a second.
The reason we're doing this, guys,
is whenever I talk to Erin, I hear my voice 2 seconds later coming back to me, and I sound boring, and I apologize for that, but it's very difficult for me to talk and not listen to myself. So that's why she's been turning off her microphone. So I'm going to ask her again to turn it back on, and let me know if you see SAS. If not, I'll just go back and bring it up again.
Hi, Fran, you're good to go.
Okay. Hey, and I have a question, Erin. Do you see my cursor, my mouse cursor, when I move it around, or do you guys not see that? I haven't moved it yet, so I'll move it around now. Do you see anything on the window screen that looks like a mouse? Message from Erin. Yes. Okay, so I get your chat messages, Erin. That's good. Okay, so let me just, I'm going to try running SAS today. As I say, I'm using my wife's computer. She has SAS on it. This is the program we've been dealing with for the last couple of weeks. So again, you had a data set called Ohana data. We read it in initially 2 weeks ago. We looked at the list of the variables names. We printed out the raw data to look at. We used proc means to look at some averages, proc freq to look at some distributions. I don't think we spent a whole lot of time on proc univariates, another way to summarize distributions. We looked at the correlation and noticed that systolic and blood pressure, as expected, were correlated. And then what we did on next is we modified that data set. We made a new version. I called it by the same name, Ohana data, but I could have called it by a different name if I wanted to. I could call the name of the second data set new data if I wanted to. It wouldn't wreck anything. But it's going to be made a copy of the original first data set I read in, which was called Ohana, way back up in the top of this line. And what we did, remember, is we took some of the continuous variables and we made categories out of them. We made a categorical version of body mass index. We called it BMI class. It was a 1, 2, 3, 4 variable. And 1 being underweight, 2 being normal weight, 3 being overweight, and 4 being obese. We broke blood pressure into a categorical variable using, if you had very high diastolic or very high systolic, you were blood BP-Cat 3. Else, if you were still high but not as high, you were BP-Cat 2. Else, if you were in the normal ranges, you were BP-Cat 1. And then finally, we decided with BP-Cat to fold in the notion that people who were on anti-hypertension medication had hypertension diagnosed in the past, and we wanted to keep them in that category of hypertension. So we defined a new variable called hyperten, which anybody who had a blood pressure at baseline, which was in category 2 or 3, or we're currently taking antihypertension medication. And finally, we broke age into 4 categories: those under 40, those in their 40s, those in their 50s, and those above 60s. And so let me just rerun all this, bring it up to speed. So I'll run that, and we have the output we saw before. I'll go back to the editor. And then we ran some programs to check the new variables we made, and then we started last week talking about different analyses. Table 1, we looked at the relationship between each of the potential confounders and the intervention variable, to see if they had different distributions or the same distributions with respect to sex and high cholesterol, diabetes, marital status. So this was the beginning of a table 1 that we would correct to show, construct, to give the reader a sense of how comparable the two groups we were comparing are with respect to percentage of men or distribution of body mass index class. We also talked about calculating averages, average age, average body mass index, average blood pressures within each level of the Ohana variable, the intervention group separately and the comparison group separately. And then finally, we moved on to table 2, which was our crude analysis, looking at a 2x2 table, looking at the relationship between the Ohana variable and our outcome death to calculate risk ratios and test the significance. And then finally, last week, we started building models. And so let me start running what we had before. We ran I'll rerun this piece again, but I think the last model we really talked about on last week was the crude model, looking at the relationship between the intervention variable and death. Let me just run that model again. So I'll look at the logistic regression, look at the model intervention. And this is where I think we essentially left off. I know we showed the preview of what we're talking about in a second, but this is our crude model. It says that we have a data set with 172 people who died and 500 people who didn't die. We're trying to predict as we have here, the risk of dying using a logistic regression model. Now, before we look at the fitted model, it gives us some fit statistics, and we'll talk a little bit about those fit statistics again today. We were talking about this -2 log L as a measure of how well a model fits a data set. We said that the smaller this number is, the better that model is fitting the data set. Because if we have a perfect fitting model, a model that gave predicted risks of 1 for everybody who died, and predicted risk of dying of 0 for everybody who didn't die, then the likelihood function would come out to equal 1, and the log of the likelihood function would equal 0. So this number, -2 log L, would become smaller and smaller as the model fits the data set better. And what this printout tells us is 2 pieces. If we look at the model with just the intervention variable, and the only covariate we have in this crude model is whether a person received the intervention or not, the value for -2 log L is 732. If we compared it to another model, the model with the intercept only, a model that gave everyone the same risk, regardless of what community they were in, regardless of whether they got the intervention or not, the value for -2 log L was 764. So our -2 log L dropped from 764 to 732, a drop of 31.9281 points by including the intervention variable in the model. That's how much our fit improved. And that number, 31.928, can be used as the basis for comparing these 2 models. The model with the intercept only to the model with the intercept and the term for the intervention variable. And that is a test which refers to as the global null hypothesis. And we'll talk about that again in another model in a minute. But notice the 31.928 was the same number we saw for the 2x2 table, when we looked at the Ohana variable as the row variable, the mortality variable, death as the column variable, did a chi-squared test. We actually got the value of 32.3 back then. That was the score test that this model was giving us. But it also gave us right under that a likelihood ratio chi-squared, 31.92, which I mentioned was asymptotically equivalent, meaning for large data sets, essentially the same as the usual chi-squared test. So all we're doing right now is repeating what we did before.